4140 steel is an alloy that has excellent strength to weight ratio. And in this video, we're going to talk about heat treatment and how that can be used to manipulate the microstructure and the mechanical properties of this type of steel. First question, what is 4140 steel? So let me just kind of take you through the terminology here and so forth. So when we say 4140 steel, there's a couple parts here. The first one is, what does the 4100 part of this name mean? So the 41. So this refers to specific series of steel. And so for this one, it's an SAE grade, which is the Society of Automotive Engineers. And the 4100 series refers to what we call a chrome moly or chromium molybdenum steel. So both of those are added things to the steel alloy on top of the iron and carbon. So here you can see that there's some variations, but we've got between a half and a whole percent of chromium and between 0.1 and 0.4 weight percent molybdenum or moly. So that's why we call it a chrome moly steel. The other part of this name is the last two letters. And this holds up in a lot of steel designations with this 4-digit number. The last two digits, here being 40, refer to 0.40 weight percent carbon. And so if I highlight here the carbon weight percents for various 4100 series steels, you'll see that the 4140 has about 4. They always have a variation here because there can be batch to batch variation, but that's the range that we need to have. So it's a 0.4 weight percent steel with chromium and molybdenum. It's also got manganese, as you can see. Phosphorus and sulfur are both impurities, and there is silicon as well. But chromium and molybdenum are what sort of separate this from other series steels. So with that, if we look at the iron carbide phase diagram, which we won't cover extensively in this video, but I do want to refer to the percent carbon because our equilibrium phase diagram here for iron carbide looks at what the equilibrium phases could be. And even though our steel is more complicated than iron and carbon, we can still use it as a way to look at phases. It still is useful for that. So if we look at the 0.4 weight percent, that puts us with this red dotted line. And so at the higher temperatures, we have a phase called austenite. That is a FCC or phase center cubic structure. And then upon cooling, we start to form ferrite. And then below the 727 Celsius, we have a mixture of perlite and ferrite. So our equilibrium phases are ferrite and cementite. Those are our phases. We'll talk a little bit more about those here in a second. And our microstructure is perlite and ferrite. So perlite being a mixture. So here's a quick picture of what this microstructure could look like. So the center here, you'll see a sort of layered structure with dark and light regions. The dark represents cementite, the carbide phase, and the lighter phase here and in the mixture as well are both ferrite. So the striped constituent here, this is referred to as perlite. So whenever you see that striped appearance, that's perlite. And the uniform phase is ferrite. So we would expect for 4140 steel having a more equilibrium microstructure to be perlite and ferrite. All right, so let's get into the other part of this equation. So why would we care about 4140 steel? What's it used for? Like I mentioned in the opening, it has excellent strength to weight ratio. So for its weight, it has excellent strength. So that means we can use less of it than other types of steels. So it has a wide range of applications. It's not the most expensive or it's not the cheapest steel, so it doesn't work for, you know, base I-beams and things like that, but it can be used for structural components, as you can see here. It is commonly used for bicycle frames, so if you have a steel bike, chances are it is 4140 steel. It's also used in automotive and aerospace or aircraft parts as well, where that strength is needed without a lot of weight. So lots of applications here for why this is important. So here in this part, we're going to go through how we can do isothermal transformations to this 4140 steel and apply the isothermal transformation diagram to predict these changes. So I'm going to open here with the 4140 steel isothermal transformation diagram. That's what you see here on the right. So this is commonly called an isothermal transformation diagram, or sometimes referred to as a TTT diagram, referring to time, temperature, and transformation. So essentially the axes, temperature, time, and then the fact that we're doing a phase transformation. So what this gives us, if you haven't seen this before, is it gives us predictive powers, right? So it allows us to predict what the microstructures will be for an austenitized steel. So that's what you're going to see in all steel TTT diagrams, when the type of treatment is done at a constant temperature. So if you see the word isothermal, that means constant temperature. So all of our phase transformations that we're going to talk about in this video are going to be done at constant or isothermal temperatures. So you'll often find that when you're looking at these diagrams, they will use letters or abbreviations to sort of simplify the layout. And so I kind of want to go through all these in case you're not familiar with this. So let's start at the top. And A refers to the austenite phase. I mentioned the austenitizing process. So that refers to making a steel that is made out of austenite. Why that's important, it is an FCC, or face-centered cubic structure, like you can see from the diagram here. So this is the higher temperature form of steel. So here you can see that it forms at, you know, around 800 degrees Celsius and higher. So austenite always refers to this A. Next, the next one you see here and over here as well is F. F refers to ferrite. This is the lower temperature iron phase. It is BCC. This is commonly what we have for iron and steels. So the BCC structure that you can see here. And if you remember from the phase diagram, this is our equilibrium room temperature phase for steel. So it wants to be ferrite. That is the phase it wants to be. All right. We also have a C, right? A C here and a C here. That refers to cementite, or Fe3C. This is the iron carbide. So this is the carbon-rich phase of the diagram. So carbon is, at least in the normal range of steels, carbon is not ever present on its own as just carbon, like graphite. However, it's usually in the form of this carbide, Fe3C. So whenever we talk about cementite, we're talking about the carbon-rich phase, and this is an orthorhombic crystal structure. And lastly, down here you see MS, M50, M90. The M here refers to what we call martensite. This is not on the phase diagram. This is what we would call a metastable, so it's not an equilibrium phase, but it is a common structure of steel that we see. It is very strong and brittle, and again, it's a metastable phase, and it's BCT, or body-centered tetragonal. So again, you're not going to see this on the phase diagram, but it's very important to steel microstructures. So let's see about, so those were the phases involved in this diagram. So let's see about the microstructure. So what it's going to look like, the appearance it's going to have, and so forth. So let's go to the top band, the top temperatures. Anywhere you see the A or austenite. This is a high temperature phase. We don't typically see this at room temperature without some sort of extra thing happening. And so we don't typically get structures or microstructures of this, but I have here what it might look at the higher temperature if we were able to record that. So just a kind of a general grain structure of an FCC metal. So in the next band below, so in this band of about 750 or even lower to about 550 Celsius, this is our perlite range, and specifically perlite plus ferrite. So you see an F here. That means that ferrite forms at the smaller or less time, and then as we go on in time, we form F plus C, and that is perlite. So this band, this yellow band that I show here, is perlite plus ferrite. So one other thing to note, in this diagram, in this TTT diagram, you'll note that it has what we would refer to as a double C or a C shape. So here's kind of a C shape, and then here's another C shape. So the band of perlite is from this top C. So again, from about 700 down to 550. So that means that as we go lower, so we go below that kind of nose here in the middle, that means that we're going to get a different type of microstructure. And this is where we have what's called bainite. So as it's shown here, so the important thing to kind of note here is that from the isothermal diagram itself, it just says F plus C, so ferrite plus cementite. So again, these are the equilibrium phases. However, instead of being in the form of perlite, it forms into this much smaller structure known as bainite. So bainite is a smaller structure, it's harder, it has higher strength, and it's got a much finer, harder to see microstructure. So we'll look at this in the slides here in a bit. And lastly, in this last band, the green band here at the bottom, so this is at about 325 or less, this is where we see martensite. So again, martensite is that metastable phase, and it also has a very fine structure of this BCT metastable phase. Very fine structure, very much looking like needles. And it can also look a lot like bainite, which I'll talk about when we look at more specific microstructures. One last thing I'll point out here. So you might notice that it says martensite start, martensite 50%, martensite 90%. So martensite doesn't always consume the entire microstructure. It's, can be about 90% or so, with the rest being austenite. So austenite can actually remain in the structure. So a lot of times if you see like lighter regions, those are potentially austenite regions of the microstructure. So now what I want to do is kind of relate this to a series of experiments that we do in our lab. And so I want to kind of go through how we can use the isothermal transformation diagram to predict structures. And so we're going to kind of go through a set of different transformations and look at what phases, what microconstituents can happen. And then in the follow-up video, we're going to look at what those microstructures actually look like and what the properties come out to be. So here I'm just going to kind of walk through how these would look. So I want to start with what we would call the quenched. And so when we talk about quenched, we're talking about a rapid cooling. So with all of these transformations that we're going to do, we have to start with austenite. And so I drew a dot up here at the top. So this means that for any of these reactions with isothermal transformations, we have to start with 100% austenite. So in this case, I'm going to go above 800. In our lab, we do 850 Celsius, but there's some differences. You can this can be adjusted a little bit, but we do 850. Anywhere above this austenite finish temperature, where we would have 100% austenite. So you typically hold for a certain amount of time to make sure that we have 100%. So that's the start. So we're assuming that we start these reactions with austenite. All right. So then the next part is the isothermal part of this. So we always want to essentially cool to whatever temperature that we want to do the reaction to very quickly. So we start at 850, and whatever temperature we want to do this reaction at, we have to get there very quickly so that there's not any type of other reactions. It's only the reaction that's happening at the destination temperature. So in this case, we actually want to get down to room temperature. We want to go the farthest down. So we want to get down here really fast, or quenching. And so that's what we do in this next step. So this red line is just meant to represent that we're rapidly cooling. So here I put, and you might notice that this says 5 down here. So you can kind of imagine we need to get down to room temperature in essentially 5 seconds. So that's very quick. That's a rapid cool. So a lot of times you might see this as completely vertical, representing that we just need to do this very fast. And so that's what quenched 4140 steel is. You just go down to the lowest temperature, and that is, you essentially hold at room temperature forever. So based on this diagram, it doesn't go through or hit any of these lines that we see up here, the C's or anything like that. And so there's no transformation that occurs as part of the dark bold lines up here. So what happens is when it reaches the martensite start temperature, which is about 350, it starts to form martensite. And martensite is essentially an instantaneous phase. It happens without any diffusion, and so it happens essentially very rapidly. So that's why you see it just represented by a horizontal line. So when you drop below 350, forms martensite, about 300, 50%, and then further on you get to the 90%. So once, if we can get down to the room temperature before hitting anything up here, then we're going to get martensite. And I mentioned earlier, but you can get some retained austenite. A small fraction of this can develop up to 10 or 15%. So that is a possibility. But for here, we're just going to talk about the martensite. So let's then go from the quenched and start kind of going up in temperature for what our isothermal transformation is going to be. So in this one, I'm going to look at what happens if we do this isothermal transformation at 360 Celsius. And so 360 is somewhere around here, and so you'll see. But the steps are the same. So I start and I heat above 800. I make sure I have 100% austenite. I rapidly cool to my temperature. So in this case, it's the 360. So again, about right here. And then this is where my isothermal transformation comes in. So again, if you look at the axis here, this is time, this is temperature. So essentially, how much time are we going to spend at the isothermal or constant temperature? And so in this case, we're going to hold. So I draw a horizontal line. We're going to hold. And initially, you'll see, and you read this just like you would a phase diagram. This initial region says austenite. This region here refers to the reaction that we see right here, right? So it's austenite plus ferrite plus cementite, sorry. And so that means that we're forming the ferrite plus cementite. So this is essentially 0%, 50%, and 100%. So at about 5 seconds, 5 to 10 seconds, we start to form we start to transform phases from austenite to ferrite plus cementite. At about a minute, we're 50% of the way there, and then a little less than an hour, maybe 30 minutes or so, that is when we have reached this line, which is the 100%, which means we have all of the ferrite plus cementite. And so in this case, like I mentioned before, this lower C shape, this refers to bainite. And so essentially here we have bainite. And specifically, people refer to this as lower bainite because it's the lower range of the C-shaped. So that's kind of important here. So lower bainite. And so that's the structure. And so I want to add one last thing that I kind of put on these diagrams that isn't necessary, but I always like to show that it's at 360 degrees. I said for roughly an hour. That's how we do it in the lab. And then after that, we have to cool it to room temperature. We're not going to hold it at 360 forever. So after that hour, we rapidly cool to room temperature. And the key here is that you might notice that it crosses the martensite start 50% and 90%. So you might say, okay, now it transforms to martensite. That is not the case. You have to remember that all of these reactions, whether it's ferrite, cementite, or martensite, start with the austenite phase, this one. So if we already have the equilibrium ferrite plus cementite, it's not going to transform into martensite. So once we're already on this side of these dark lines, right, that material is not going to transform to martensite. So we would just have lower bainite, and there's no change when we go from 360 to room temperature, at least from a phase perspective. There's no change in phase. All right, so again, we're going to go up in temperature. And so the next one I want to hit is 460. We do this in the lab, and so I think this is another useful one to see. So start the same way, start at austenite, rapidly cool to 460, hold there. And you kind of get from the perspective of what we're doing. We're trying to fully transform them at the temperatures we're at. So here we need to go to, again, about an hour before this fully transforms. So the overall process is the same, goes from austenite to austenite plus ferrite plus cementite until we just get ferrite plus cementite, right? Like about an hour. The only difference, as you'll note, I've wrote over here, instead of the lower bainite at the 360, we have what we call upper. So on the upper end of this temperature range, so this C shape, if you're forming bainite, we call it upper bainite. It has different properties. It's harder, it's stronger, and so we give it a different name. And again, we quench or cool to room temperature, and that shouldn't involve any change if you've fully transformed. All right, so now you'll see the next one we're going to look at is 620. And so we're up here now. And so we're above this nose of the curve, right? And so this is no longer going to be bainite. We're going to get a different microconstituent. So perlite, if you remember from the previous section. So same process, heat to 8 or 850, get 100% austenite, quench to your temperature. So in this case, we're going to 620, so right around here. And then we hold for the appropriate amount of time. And about an hour is good here as well. Or you can do 2 hours to make sure, because you want to make sure you cross and get the whole thing if that's what you want your microstructure to be. And so in this case, we're on kind of the lower end of this C shape. And so we would expect to get ferrite, and our main component is going to be perlite. And you might notice I have the word fine here. So on the lower end of temperatures, when we get perlite, it's still perlite, it's still layers of ferrite and cementite, but we put the fine designation there because the layers are closer together. They're smaller layers closer together. And so we call this fine perlite. So the layers can change with the temperature. So we're going to see that, and we're going to see why we do multiple temperatures in this range. So this would be fine perlite plus ferrite. And again, we quench to room temperature with no change. So next, we want to go to 660. And I'll kind of show why we want to do this. So at 660, we're somewhere around here. I'm using approximate temperatures on the diagram. I'm doing that. So we go to 660, and again, we hold. Here you'll notice that we're at this kind of nose of this C, the part that juts out the most. So this reaction starts the quickest of the perlites, right? We're right in the middle. And so this starts after about a minute and finishes well before an hour if this is the case. So we don't actually need to go more than an hour in this case to get this perlite. So this is again going to be perlite, and like I mentioned in the previous slide, the layer structure can vary with temperature. So as we go up in temperature, the layers get thicker, and so we're going to call this the medium perlite because it's kind of in the middle of this temperature range. So we get medium perlite, and we'll still have the ferrite phase as well. And then a quench to get down to room temperature. All right, the last one we're going to do and talk about in this kind of experiment and progression through different microstructures is we're going to talk about 700. So same thing, start above 800, quench to 700 very quickly, and then hold And in this case, we're going to need to hold for 2 hours or so. So here at 700, one thing you're going to notice is, again, we can kind of go through the same progression. So at this point here, within a matter of 10 seconds or so, it's going to reach this region. So that means that ferrite's going to form. So that is ferrite in the structure. So ferrite plus austenite. And then we keep going, and you'll see that it takes a while in this case. So we're at about 2 minutes now, where we start to cross this line. So this is where we have austenite plus ferrite plus cementite. So here we just formed ferrite, and here is where we're forming perlite. And so that reaction takes quite a bit of time. And so you can see down here at about an hour or so, we've potentially reached full 100% of that structure becoming perlite. So we have ferrite plus perlite. And you'll notice here that we're on the upper end of the C shape. And so this takes quite a bit of time to do. And we're really close to where this reaction doesn't take place, or it takes a very long time to take place, as you can see by this curve that we have here. But we should see coarse perlite. So again, it's got the perlite structure, but it's got thicker and thicker bands. So this is going to be our coarsest, so we call it coarse. And I just want to emphasize here, there's no cutoff that says there's a fine, there's a medium, and a coarse perlite. It is a gradient from one to the other. And so we're just kind of calling them that in this example, but it's a gradient between thinner bands to thicker bands that we have here. So this will be coarse perlite plus ferrite in this example. And so we'll quench to room temperature. So I do want to make one kind of quick note here, is that let's say we have a furnace that we're doing this experiment with, and there's a little difference in the temperature. So let's say we maybe, instead of at 700, we're actually up at like 725 or 750, closer up here that you see here. So when that happens, something interesting can happen, right? So essentially we don't catch this reaction that we're seeing with the dark lines. We just form maybe ferrite, but we still have austenite. And so what happens if we're in that region and we never form perlite, what happens is that when we do this quench, so when we do this final quench, we would actually form martensite. And martensite has a drastically different microstructure and mechanical properties. And so we can always tell in the lab when this goes wrong, because up here you might notice that we have hardness. So this gives you a rough idea of the hardness. So this coarse perlite should have a hardness of around 10 on the Rockwell C scale. But if you notice down here, martensite can have a hardness all the way up to 60. So if the temperature is even off by a few degrees in the furnace, we can actually see this sometimes. So sometimes instead of getting a hardness of 10, we might get somewhere up close to 60. So that's one of the things that can happen. So in this next part, then we're going to look at how we would, we're going to look at the results essentially. So we're going to look at the microstructures that are actually present, and we're going to look at the mechanical properties that result from each of these different transformations that I've laid out.